Well, hello, everybody, and welcome to another edition of our Akka.net community stand-up. My name is Aaron Standard, and I'm joined here by my colleague, Gregorius Sodharmo. Gregorius, how are you doing
Hello.
today?
Oh, pretty good. Thank you. And how about you?
No complaints. Ready to dive into some of our, let me go ahead and change the layout a little bit here. Ready to go ahead and dive into some of our recent Akka.net releases. Hey, Houston, good to see you. Let me go ahead and grab our little banner here. All right. We're going to go ahead and cover some recent Akka.net releases. So I guess the first thing we're going to do is talk a bit about the EventStore plugin. Let me pull this up real quick. So EventStore has long been a popular choice for building Akka.net applications. It dovetails quite nicely with the event-driven model that Akka.net exposes at the application layer. This kind of gives you a database oriented version of that same type of programming model. However, the Event Store plugin has bite rotted pretty massively. It hasn't really been maintained for several years. It was never really kind of an official Akka.net plugin. Me and Gregorius never really worked on it at all. However, one of our customers, that would be Matthias Jacobson and his team at Digital Creation, and I think it was Matthias personally who did this, rewrote the Event Store plugin to use the gRPC client. It's kind of the new modern client they've been using. And the plugin is now fully current with the most recent versions of Akka.net. I believe they're using it in some of their own production projects. So big props to Digital Creation. If you need anyone to help you build an Akka.net application from scratch, I know the Digital Creation team has done that for a number of their customers and spaces like banking and that sort of thing. So definitely feel free to contact them. You can go ahead and find them at digitalcreation.se. Next, Akka.hosting 1.520. So this was a fairly small release that we did, mostly trying to get the Akka.net 1.520 distribution out there, since this actually has some important fixes that we're going to talk about. But the other thing I've been working on is I've been trying to make some improvements to the logging experience for Akka.net in a few areas, and we're going to touch on that again later today as well. But one of the things I did here is I just made it a lot easier to specify the default log message formatter. So if you want to do things like enable serial log formatting across the board, that's now really easy to do. There's a built-in method inside the logging config builder that will let you do that. Let's see. Next, Gregorius, we've got your fun project that's been taking up a fair amount of the week. Dealing with common vulnerability exceptions in NPG
Yes.
SQL. Take it away.
Yeah. So we have a user in Discord who notified us that there was a CVE posted on PostgreSQL, basically. So what we did is that we bumped the minimum version of PostgreSQL that we use in Akka.Persistence PostgreSQL to 8.0.3 and then released the 1.5.20 version for PostgreSQL, just to find out that a few hours later that the Postgre maintainer actually backported all of their fixes back to version 5. So we are now in process of rolling back all of that to version 5.0.18, which has the CVA fixes in it. And maybe we'll release 1.5.20.1 in the near future.
Yeah, so we're kind of playing historically with this plugin. We've always had to play a bit of whack-a-mole with the version of the NPG SQL driver that we use, because you have users that are using Akka.Persistence Postgres and others that are using like Entity Framework with Postgres under the covers, and they support like different versions of the same driver. So we've always supported a version range. Well, we got rid of it in order to basically resolve the CVE, and that caused some problems for people who are using a couple of other NPG SQL plugins. Now it looks like we didn't need to do that if we just waited longer, I guess, to solve the CVE. So
Yes.
I always say to people, incentivize the behavior you want to see more of. Well, if you want to incentivize us to respond to CVEs quickly, this is not how to do it. We're gonna I guess we're just going to go ahead and wait and see next time there's a CVE in one of our dependencies and say, all right, well, you know. Sorry about that. Looks like I bumped my microphone by accident. I was having some trouble with this on my Akka.net training yesterday as well. Gregorius, can you still hear me okay?
Yes, but I think you're using your webcam mic instead of your big microphone.
Yeah, let me fix that. Audio. Yes, you're correct. All right. Well, I'm just gonna get a mixer box for this thing, so that can't happen anymore. Those USB connections are pretty flimsy. All right.
Mhm.
Right. Long story short, we're probably going to be a little slower to respond to CVEs if we support a package range next time. Although with things like the only other things we support package ranges on are the Microsoft and extensions packages, and those fall out of support pretty quickly, like every couple of years. So maybe we'll just go ahead and move forward with that. Speaking of Akka.Persistence SQL releases, you also shipped Akka.Persistence SQL 1.520 recently as well, Gregorius.
Mm-hmm. Yeah, there's nothing really major from us on this release. It's basically just dependency updates. But Drew did contribute a optimization in the length tick and variable captures inside the code, so it should be running slightly faster now.
Yeah, it should fix a couple of memory issues there and a little bit of throughput as well.
Mm-hmm.
All right. Next on our list, we're getting to the big releases now. We've got Akka.net 1.519, which we shipped. I guess we did not do an April community stand up. This would have been like the day after we did the April one. The big fix here was one of yours, Gregorius, which was fixing this
Mm-hmm.
contention problem. Well, actually, the two big
Yeah.
fixes, but this one.
This is a very spooky compiler optimization problem between the new async await and the old threading model. In this case, we're using the countdown event that probably uses semaphore inside of it, and that just isn't playing well with await task async that the new Microsoft is using. So it somehow created a resource contention during timer startup. Like you can see in the output right there, it's actually waiting for like 5 seconds for the timer to start.
Yeah, and is that how long it takes the timer to start, or is that how long it takes the call to the timer to complete?
No, that's the start of the timer itself.
Got
Like
it.
it kind of hung
Yeah.
while starting.
And we did notice some deadlocks outright as a result of this code as well too, right?
Yeah, but that was fixed in 1.5.20, which you actually found later.
Well, there was some deadlocks of the resource contention here where the timer could just straight up hang. And then yes, we found some crashes in
Mm-hmm.
1.520 also related to this that we fixed. The other deadlock issue that we found was actually in the Akka.net test kit. So this one I took care of. Basically, the old queuing structure that we had in here was basically kind of something left over from the synchronous days of the test kit, and it was kind of rigged together with baling wire and duct tape. We replaced it with channels, and now we don't have deadlock problems anymore with the async test kit. So there was all sorts of spooky async await side effects there. And then we did 1.520 more recently.
Mm-hmm.
And this is basically where I fixed. So one thing I did that was important for the thing I'm going to be doing on our show and tell, which as Houston's sitting here, spill the MQTT, which clever. That's going to be our little show and tell today. But we fixed a couple of important bugs here. One was this Akka Streams fix. I'll get into that in a second. The other was piggybacking off what Gregorius worked on. I noticed while working on TurboMqtt that there were periodic crashes happening where I would go ahead and see if I scroll down, the hashed wheel timer was in an illegal state. This was another spooky side effect. And I think it was Andrew who found this problem. This comes from feeding a volatile variable into a switch statement, where basically we fell into a case that was never possible inside the system. Where this value, if it's set to state one, is a valid state. Therefore, how could it be in an invalid state? And this is basically spooky side effects from the way we use the volatile keyword. We fixed this by just assigning it to a local variable first. But anyway, that got fixed in 1.520. The other thing we did was that, and I want to apologize to every Akka Streams user who's ever tried to log anything inside a stream stage. This feature of Akka Streams was like 100% unusable prior to 1.5.20. And the reason being is that every single Akka Stream stage, all of its logging looked like this. Down here, it was all log source and then the URI, local URI of the actor system. So there was no way to tell which stream stage was logging what. We have since fixed this. So now what you'll go ahead and see here is you'll see the name of the shape. You'll see the name of the inlet or outlet that's doing the logging here. And then finally, we'll also include the path of the materialized actor that's running the stream stage. So you know roughly where in your actor system this logging is happening. So we made the default log source much more verbose than it used to be. We also made it so if you customize the log source, there's a property you can override in a custom stream stage. We actually correctly use that now, whereas we were not before. So again, mea culpa to anybody who's ever tried to log anything inside an Akka stream stage. This was total garbage prior to 1.5.20. Now it actually works correctly. So big quality of life improvement there. I think that gets us through all of the stuff we've done so far. Let's go ahead and talk a little bit about some of the upcoming projects that we're working on. This Stack Overflow question prompted some introspection from me on some of the projects that we want to take care of. Namely, what they were complaining about is that they still have to call getLogger.serialLog logging adapter in order to do things like add context enrichment to serialog down here. Sure enough, I took a look at the serialog code and found that, yeah, we really haven't tried to address this at all. I think we can take care of it. So that way, if you call with context or whatever, you don't need to do get serialog logging adapter to do it. We should just make it just work for you behind the scenes. So that shouldn't be too major of a change. I'm going to spend some time this week trying to get that done. The other big feature that we've had available as a draft for a while. This pull request isn't passing right now because I haven't done API approvals yet. But we added a log filtering feature to prevent Akka.NET logs from being emitted in the first place. This basically uses some like wildcard and pattern matching syntax to do things like, if I scroll down here, let's review one of my examples. Let's dig into here. Let's take a look at my logger spec. Well, I guess that's actually fine. Let's do the log filter evaluator spec. Here we go. Okay, I have a log filter builder, and I'm going to say exclude any logging source that contains Akka.tests and exclude any message containing foo bar. So the idea is that I can filter out logs by source. I can also filter out logs that contain a specific bit of text inside of it. So that I'm basically in buildings. And by the way, in order for a log to be filtered, it only has to match one of these rules. So if it matches any of these rules, the log's gone. And so the idea here is that I can feed this into my actor system by using this little logger setup right here. So what this is going to allow me to do is say, okay, if I go ahead and I create a logger with this basically log source or this log source, and I go ahead and I write out, a warning from this log source here, that's going to get filtered out automatically. If I go ahead, this source right here is not filtered, but this message is, that'll get filtered out automatically as well. So a couple of things worth mentioning. The way this works is by basically evaluating the logs as they're being written out to the logging actors under the covers. So some of the third-party logging libraries will need to be updated to support this feature. If you use filters based off the log source, that can be done very performantly. It doesn't require expanding the log or doing any of the formatting. That's kind of the expensive part. But if you have to filter based off the content, the log message, that's going to be more computationally expensive. So the actors that are basically responsible for processing log messages are going to be using more resources. If you're filtering based off the content of the message, nevertheless, we want to support a wide range of features here. This functionality, if we ship it, is going to make it into Akka hosting. So this should be done via that sort of the logging config builder API. And we're planning on shipping this in the next release of Akka.net 1.521. I'll drop a link to this in chat, but it's basically the second pull request open from the top here. You have 48 hours to weigh in on any API or design changes that we should make, or this is shipping as is into the framework. So just consider this to be your warning. Go ahead and comment now, forever hold your peace, because this will become part of the standard API in not too short a time. And I think that does it for new Akka.net releases. So that brings me to our show and tell, which should be relatively brief. We're going to talk a bit about TurboMqtt, which is a new MQTT library that I've been working on. Gregorius, you've been helping me with this as well. So let's go ahead and pull that up real quick. So I'll drop a link to this in chat. Hopefully I don't unplug my microphone again by accident. Let me go ahead and mention this here. So this is our TurboMqtt library. Now, I've got a little PowerPoint. We're doing a series of videos on YouTube on how we built the fastest MQTT.NET client with Akka.NET and Akka Streams. I'm not going to go through all of it here. The first video should be airing actually in a couple of days. I'm working on shooting episodes 2 and 3 right now. But if you're not sure what MQTT is, this is an Internet of Things protocol primarily. It stands for the MQ Telemetry Transport. It's part of the OASIS standards. OASIS is the same body that decides what's in AMQP, which is what ActiveMQ and RabbitMQ use as part of their sort of messaging protocol. This is a much more lightweight messaging protocol, though. It's designed for devices that are operating out in the field with limited bandwidth. So the use case that prompted us to basically start looking into building our own MQTT library is in the meter data management space. Now, this is not a meter data management example, but it's close enough. In this case, you might have something like a temperature sensor. So we also have customers in fields like oil field management. An oil field pipeline would have temperature sensors installed every yard or so on it. And this is responsible for being able to measure volume and also being able to measure viscosity and other things that all matter for like the smooth operation of like an oil pipeline. So these temperature sensors might transmit data using a relatively low bandwidth and kind of a lossy transmission medium. Usually it'll be something like short field radio, like RF signals, that type of thing. Those signals will usually get picked up by a gateway or picked up by some device that's actually connected to the internet. Those responses will all get aggregated and transmitted via the MQTT protocol to an MQTT broker. This MQTT broker is actually like a full-blown server that runs in a data center. It's responsible for taking all the MQTT data, which is associated with specific topics, and publishing that data to all of these subscribers that are interested in those topics. So in this case, we might have a bunch of, another mobile device or a backend system that are all interested in knowing about what's the temperature of this sensor at this stage in the pipeline. And this might power things like real-time monitoring systems or whatever. The application that we were getting asked to kind of look at is a meter data management problem. This is something that a public utility company has to do. So if you're a power plant operator, or maybe if you operate, let's say, a water distribution network, this is a problem that you have. You might service, let's say, 1 million plus buildings. Some of them could be homes, could be commercial, could be a blend of both. Doesn't really matter. And these smart power meters or smart water meters operate using, let's say, RFID signals. Those RFID signals will be aggregated by gateways that are installed in close physical proximity to the buildings themselves. That way, it can actually aggregate the signals and then transmit them either over a cellular connection or maybe a hardwired internet. It kind of depends on how the infrastructure is set up. But these gateways are doing the transmission to an MQTT broker. In this case, we're using like an open source broker, EMQX. There's other technologies that can do MQTT brokering, NATs. I think RabbitMQ can even natively support it. ActiveMQ can support it. There's a number of different technologies in the space that can all do this. But these brokers, the sort of the requirement that we were given by a customer that was interested in trying to build a meter data management solution was that for capacity planning purposes, they had to account for the worst case scenario. In terms of peak load, which is every gateway all reporting their meter readings from their respective homes all at once. So 200,000 meters, 200,000 gateways, each one connected to, let's say, 5 to 6 homes, all reporting in with a meter reading at the exact same 15-minute interval. Now, this user had already done a bunch of other normal things you should do to try to mitigate this type of problem. They had staggered all the gateways so they wouldn't report all at once. I had recommended that they try to do things like compress data so that way the actual packet size gets smaller. So they were looking at doing all this stuff. But if you're rolling out a big piece of physical infrastructure, like 200,000 gateways and a million smart power meters, and then you have to have them all point to a shared set of infrastructure, that's not an easily reversible change if you do something wrong. So you have to have a lot of headroom built into how the system designs from the very beginning. If someone starts squealing about premature optimization when facing a problem like this, you are going to create a real operational problem that's very, very expensive to fix and involves a lot of human labor to do it. So you've got to basically capacity plan super aggressively to make this work. So what this user thought was responsible was being able to go ahead and handle worst case scenario, every gateway reports in at the same time. And that load was going to be spread out across 3 to 5 consumers. So if you have 5 consumers, that means each consumer needs to be able to pull about 40,000 messages a second coming off of the broker. Well, we went ahead and were given a proof of concept from this customer built on top of MQTT Net, which is the most popular dedicated MQTT library in the .NET ecosystem. And so, we were running this at quality of service level 1. MQTT supports a configurable quality of service. QoS 0 is at most once delivery. Works the same way Akka.NET messaging does. It's all fire and forget. QoS 1 is at least once delivery, where you're guaranteed to get the message, but there might be duplicates. And then there's quality of service level 2, exactly once delivery, which basically the higher the quality of service, the more round trips there are between the publisher and the broker and the subscriber. So it gets more complicated the higher the quality of service goes. This user wanted to run with QoS 1. So we went ahead and we tried stress testing MQTT Net using the customer sample. And this is with about 1100 kilobits is about the size of not 1100 kilobits, 1100 bytes is about the size of the payload. So it's basically a JSON payload representing multiple pieces, multiple meters all reading in at once. And we were able to get to about a peak performance of 12,000 messages a second doing this. Now, some of the performance numbers we saw were actually EMQX's fault. It's designed to allow a very small number of in-flight messages to be out for delivery at any given time. And when you exceed the default queue size per topic, which is only 1,000 messages, it starts dropping the subscriber for some insane reason. So as a result of that, you end up basically with a lot of message loss. So Gregorius and I reconfigured EMQX to allow up to the theoretical maximum of messages to be in flight, which was whatever the ushort.max, whatever that value is, 65,000 something. And we also let the queue size be up to 1 million queued messages. So that'll result in EMQX having a lot of stuff in memory at a given time, but it'll help ensure that things get delivered relatively quickly and that the system does not abort the client when things get busy. So here's what we noticed. Back pressure started to build pretty quickly inside the MQTT Net client where it stopped keeping up, and eventually it would tip over and fail. Particularly if we didn't adjust EMQX's settings. But with that, we still noticed that back pressure became apparent pretty quickly. So we evaluated a number of different options for trying to solve this problem. We tried changing a whole bunch of settings in MQTT Net. We tried using their low-level client as well. And ultimately, where we came down with this was that we could probably, in the span of about a week, about 40 to 50 hours of engineering effort, we thought we could probably beat MQTT Net on performance. So we did. And some of the design decisions that we made was we were going to use system.memory for packet encoding and decoding. Now, this is pretty obvious to anyone who's been working with .NET for a while that you should use system.memory if you're doing a lot of low-level, byte work. But what's not obvious is the choice to use a packet size estimator, which is the ability to, before you serialize a packet according to the MQTT specification, this allows us to, with 100% accuracy, predict how big that packet's going to be long before we do any encoding. the reason why you want to have a packet size estimator, why this is a useful piece of technology to have, is it allows you to take advantage of buffer pooling on the right side of your application. So if you're having to write lots of packets, particularly if they're small, this will allow you to predict, okay, what's the total buffer space I need to get every single queued packet that's currently going through my Akka Streams pipeline out onto the network in a single flush. Packet size estimation is necessary for doing that. This is one of the things that we're going to try to do with Akka.NET serialization down the road is leverage packet size estimation as well. That allows us to take advantage of right side buffer pooling. I should note on the read side, and this is going to be true for Akka.Remote as well in the future. On the read side, it's actually not tenable to use pooling for that. And the reason being is that unlike, let's say, ASP.NET, where requests have a definitive beginning and end, when you're working with just raw packets that you're serving up to an end user, it's actually not possible for the framework author to determine when that message is done being used without implementing something like a reference counting scheme. And I've tried doing that before, and it's very easy to screw up. So you're better off actually just newing up a byte array when you're doing decoding, when you're basically taking packets off the network and serving them to the end user. But for the right side, pooling is totally possible. Akka Streams was going to basically be the big star of this show, using it for I/O batching, especially on the write side, but also on the read side as well. Encode packets into groups when we can. This allows us to use a smaller number of system calls to write messages out to the socket. That's a technique we implemented in .NET with Akka.Remote a long time ago, and it improved the performance and the stability of Akka.Remote's speed a lot when we did that. That's a good practice. You want to basically do system calls as infrequently as you can and make sure you have a lot of data that's ready to get flushed each time you do it. But you don't want to wait a long time between system calls either. So generally, when one system call ends, you want to start the next one, but you want to make sure that while your previous system call is in flight, you're taking advantage of the downtime to go ahead and buffer things together. That's exactly what Akka Streams does naturally without us needing to do anything special. The other thing we decided to do is that most of the MQTT clients in .NET, we actually evaluated a second one in addition to MQTT Net. They both use like old school event handlers in C# for being able to notify the client when a packet's available for processing. I thought that's kind of like dated to some extent. And since we have system.threading.channel now, maybe we could go ahead and expose the MQTT packets being pulled off the network as a stream that you can actually reason about and do things like process as an IAsync enumerable. That would probably feel like a more controllable and handleable way of dealing with, let's say, the flow of traffic than having a event handler where every single packet is treated as its own unique special snowflake that way. Finally, we actually used Akka.NET Actors for handling the more complex protocol. So this is for quality of service 1, quality of service 2, all of the ACK-NAC workflows that have to take place to make sure the broker recognizes that a message has been fully published or has been fully processed. We have actors that are responsible for taking care of that out of band. That way we don't block the flow of traffic inside our MQTT client. Then finally, we wanted to make sure we took advantage of async enumeration for socket reads and writes. Basically, we're using system.io.pipelines for being able to pull data off of the socket and flush it into our channel. That's going to ultimately result in the user receiving the message. But on the right-hand side, we're actually consuming from a channel that has the packets and, well, actually has the a memory pool that has a bunch of packets encoded into it and an estimate for what the total size is going to be when it gets flushed to the wire. That's ultimately what we ended up building. And from a performance standpoint, this is at quality of service level 1 with the same size packets we're using before. The peak load we were able to kind of observe here was about 70,000 messages per second rather than 12,000. So significantly improved performance. But on top of that, and I'll go ahead and bail out of my PowerPoint real quickly. On top of that, if we go to the performance figures, in fact, I've got some new ones that I've been working on right here. We were able to go ahead and hit about 225,000 messages per second, running at quality of service level 0. It's the lowest level quality of service with a payload size of 10 bytes. I guess I need to go ahead and grab my other set of we actually updated these benchmarks yesterday, but I'm also able to achieve this exact same performance, about 225,000 messages a second. I'm also able to do that with 1 kilobit messages as well. And the reason why I kind of asked about this on Twitter yesterday, the reason why performance starts to break down after you exceed about 1 kilobit in the message size is that you're actually exceeding the TCP maximum frame size in terms of how big trying to remember what the exact terminology is for it, but basically the maximum sequence size that a TCP packet can encode. So you're resulting in basically the lower level of IO. This is the operating system level TCP socket stuff is going to start fragmenting your messages and transmitting them in more pieces the larger it gets. And that's going to result in your requests per second starting to drop. So you start basically going over a natural size limit enforced by TCP at that standpoint. We are planning on working on a quick base transport, which uses UDP under the covers and therefore may not be subject to those same sort of size limitations. But usually though, over the open internet, you're very unlikely to be able to send the theoretical max UDP datagram size, which is about 64 kilobits or so. You're unable to usually transmit that reliably over the internet because all the various switches and routers and other devices you're connected to, not all of them are configured to support that big of a packet size. So typically your max UDP packet size has to be a little bit smaller. I'm sure Quick has some sort of equivalent to that maximum frame size as well that it enforces. But long and the short of it, we are significantly faster than MQTT.net. MQTT.net, according to our benchmarks, and you'll see this in the video that I published, for a 1100 byte message, does about 45,000 messages a second at quality of service 0 versus the 225,000 that we're doing. So one thing I wanted to pull up while we're all here is actually go ahead and grab some of the source code for MQTT.net and take a quick look at it. The most interesting stuff here is actually going to be the Akka Streams code. Now, by the way, this is also the first project where I ever actually used code coverage in a meaningful way, mostly to make sure that we were covering all of the persnickety details that go into the MQTT protocol. And for those of you who are familiar with MQTT, right now we only support 3.1.1, which is one of the two major there's, I guess, 3 major standards that are all heavily adopted right now. This is one of the big ones. MQTT 5 is the newer one. We chose to support this one at first because that was what our client needed. And then on top of that, it's simpler. MQTT 5 added a whole bunch of new optional fields that have to be encoded. We will support all of that. That's on our roadmap, but we just haven't implemented it yet. We also have not implemented TLS yet, which is on our to-do list. This is an example of what the outbound processing pipeline looks like for MQTT, Turbo MQTT. We have a client ID. We have the transport. This transport could be TCP. We also have an in-memory transport we use for testing. We will also eventually have a quick-based transport as well. That'll use the MS Quick libraries under the covers. We have our memory pool that we're going to use. This is right now just the default memory pool. Maybe we'll get cute and use a custom array pool or something here. We have a max frame size. This is basically how big all of the frames being flushed to the socket can be. This is a TCP setting. We have the maximum packet size. This is how big an MQTT packet can be. This is something you negotiate when you connect to a broker. And then finally, we have a flagged whether or not we can enable open telemetry. You don't directly interact with this. This is all kind of determined via the settings class that you pass in. But since we're all Akka.net fanboys here, I figured I'd show it. We are going to create a sync from the channel writer that the transport supports. So that's going to be our final sync that we write out to. We are going to create a little flow here that takes a MQTT packet. If I go in F12 on this, all of the various packet types that are supported by the MQTT protocol all have their own implementation of this base class here. So we have the connect packet, connect ACK, then the more popular ones, publish, puback, pubrel, pubcomp, all that good stuff. We'll cover the details of that in a subsequent YouTube video. But down here, we have our open telemetry flow for measuring packet rate. So what's the rate of all the different packets we're writing and for this specific client? I've done a little bit of testing using .NET Aspire for this to go ahead and make sure all these numbers make sense. Aspire has a couple of bugs with the way it does open telemetry right now. For some reason, when I'm running with multiple clients, I can't actually select all of them on there. But I've double-checked the numbers in Prometheus and Grafana, and that works there as well. Then we have our encoding pipeline. This is doing all of the memory pooling, all that good stuff. And then we also measure bit rate. The ultimate measure of speed for something like MQTT is not the number of packets, it's the number of bytes you're transmitting. So we record that separately as well as a counter type down here. And that gets written out to the transport. The underlying transport is going to read from the reader that's connected to this channel here. And that's going to be what determines the rate at which we flush out to the socket. Now, one thing that's kind of funny is that we're doing a little bit of composition with Akka streams. This is our encoding stage, which we test separately. And for our encoding stage, we are going to select the packet that's being processed, and then we're also going to compute the MQTT3 packet size right here. And this packet size estimator is going to basically check which version of the protocol we're using, and this is all being done using MQTT 3.1, 3.1.1. It's going to compute the size. We have a little packet size filter here that's going to drop any packets that are bigger than the allowed maximum. And then this is the really fun part, this batch weighted stage right here. This is going to allow us. So by the way, batching in Akka streams only takes place when there's back pressure. So whenever the underlying Akka.net, well, not Akka.net, but whenever the underlying transport is busy doing IO, we're going to have back pressure on the channel. And that's going to mean that we start batching when this occurs. So we're going to go ahead and batch as big as the maximum frame size. The cost function for a batch is going to be the estimated packet size. And then we're going to basically aggregate all of the individual packets we want to publish. We're going to aggregate all of them into tuples right here. That's what we're going to do. And then finally, at the very end, we're going to group all these packets into a single frame using the MQTT encoder flow, which is where the actual encoding into byte arrays goes at the very end here. So that's that on the right side. On the inbound side, when we're decoding packets arriving from an MQTT broker, we are going to basically create a channel source from the transport's reader. The transport is going to basically take any bytes that it pulls out of the socket and is going to flush them into our reader right here. We're going to measure bit rate down here, and then we're going to feed this into our decoding pipeline. This decoding pipeline is going to be responsible for, if I go down here, this is like a custom Akka streams graph stage, is going to basically grab this buffer. And let me see if I can find, here we go. We have a little decoding class right here. This decoding class is going to take care of parsing all the packets. It's going to deal with things like partial frames as well. That all gets handled in there. And we're going to emit an array of packets that we parsed out of this byte array here. We're basically kind of working in batch. Then down here, by the way, we have this async call right here. This is super important for performance reasons. The reason why this is important is this inserts a new actor in the processing pipeline. So this acking flow, which is responsible for automatically acknowledging higher quality of service packets and other packet types that require acknowledgement, such as subscribe and unsubscribe packets, we are going to basically do all the acknowledgments here. This allows decoding and acknowledgments to run asynchronously from each other inside separate actors. The decoding pipeline and the acking pipeline both have a bit of overhead associated with them. This allows them to be temporally decoupled from each other. This basically created like a 4x improvement in the total rate of throughput for TurboMqtt when we did this. Finally, down here, we have our basically a little bit of filtering. We're basically converting this packet into a, what's it called? Converting it into MQTT message, which is the data type that the end user uses to interact with the TurboMqtt directly. And right now, I was just debating this with Gregorius. We have a packet deduplication flow designed to prevent duplicates from being sent to the end user. We're considering getting rid of this because the heuristic it uses is using what's called an acknowledgement buffer. The problem with it is that packet numbers repeat. They're not monotonic, in other words, because they're like kind of limited to a short unsigned integer. So packet numbers can repeat pretty frequently if you're using a fairly fast producer. Therefore, you might accidentally, you're likely to have a false positive with the deduplication system if things are happening really quickly. So we're kind of planning. I think the plan is we're probably going to get rid of the deduplication flow. It's not currently shipped inside the current version of TurboMqtt. We just think that for really slow moving systems, this doesn't help you all that much because the packet expiry window is like 5 seconds. And for really fast moving systems, it's more likely to create a problem than it is to solve it potentially. So we're probably better off making the end user be responsible for deduplication in the grand scheme of things. From the end user's point of view, if I go to one of our samples, let's take a look at a consumer sample real quick. This is one of the samples we use to do some performance testing. This is basically just kind of a dev null consumer. But the way you work with TurboMqtt is, in fact, I'll go to program.cs here. Let's see. We go ahead and we call this method add TurboMqtt client factory. If you already have an Akka.NET actor system installed inside your service collection, we will reuse that here. If you don't have one currently installed, we will instantiate an actor system and use that to basically create all the different TurboMqtt clients that you might end up needing. Down here, we take the MQTT client factory as a dependency in our constructor. And I am going to create an MQTT client TCP options configuration class. This is going to have the host name and port of the broker we're connecting to. And then we have our MQTT basically session options here, where we're going to specify here's the version of the protocol we're using. Here's our client ID. Here's our login information. Here's how long a keep alive should be. And we're also going to pass in the clean session flag, which basically causes the broker to forget about any previously unpublished messages that might have been intended for the subscriber. This basically tells the broker, don't bother. That's what that's for. We then call client factory.create TCP client, and we will get an MQTT client right here. In fact, I'll go ahead and make that explicit. And then down below, I call connect async right here, and we'll go ahead and get a connect result back. If the result was successful, we will basically just continue. If it's not, we'll bail out. And then finally, down below here, we can subscribe to the broker. We'll go ahead and call subscribe async, and we'll pass in the topic name and the quality of service we want. We also have an overload that allows you to basically specify multiple topics if you want to subscribe to several all at once. But this is kind of the simpler way. We're going to subscribe, and if the subscribe operation was successful, then we have down here, in fact, I'll go ahead and make this explicit as well. Channel reader, and it's MQTT message. The API for consuming messages from TurboMqtt is a system.threading.channel. And specifically, it's a channel reader. So we'll call wait to read on the channel, and we'll await on that. And then while we're able to go ahead and read, we'll go ahead and read out. And every 1,000 messages or so, we'll go ahead and just record a message out to the console like that. And that's sort of what the read side of TurboMqtt looks like. On the publishing side, if we go over here, let's see. We're going to create a brand new MQTT message with a topic and a payload. The payload's all just basically a read-only memory segment. We're going to go ahead and create some payloads. And this is after we have presumably connected successfully to the broker. We're going to call publish async, and we will get a publish result back. If you're operating with a quality of service higher than QoS 0, that publish async operation will only complete when the broker has sent us an acknowledgement packet back, letting us know that it's fully received the message. So we have some actors that are there designed to make sure those tasks complete. One thing we're probably going to do is also allow you to turn off auto acknowledgement for receiving packets. That way you can basically decide to manually acknowledge them when you fully processed it. This will allow the MQTT broker to be able to do things like reliable delivery without you having to worry about messages going missing if you want to. We just didn't implement that the first time around because our customer was fine with auto acknowledgement. But we're going to go ahead and add manual acknowledgement for people who are really concerned about making sure they fully process every message before the broker forgets about it. So that's the basis of TurboMqtt. You can go ahead and find out more at the repository up here. Like I mentioned, we're going to be doing some more YouTube videos on it. First one should be coming out in a couple of days. And it's been a really fun project for me. It's allowed me to discover a whole bunch of things we need to fix with Akka Streams logging. That's kind of what prompted some of those fixes that went into 1.520. So it's always good to eat your own dog food. And I got to say, let's go ahead and take my Akka.NET maintainer hat off for a second and put my Akka.NET user hat on. the amount of stuff that like MQTT net has to do, the client that our customer is originally using, to basically handle safe async concurrent programming stuff is completely difficult to reason about compared to how smoothly Turbo MQTT works. And it's precisely because of that one message at a time processing guarantee that Akka.net has that radically simplifies all of this. This isn't the first time I've built a driver on top of Akka.net before. In fact, I think we have a pretty popular Zipkin driver, if I'm not mistaken, petabridge.tracing. Yeah, we have a pretty popular Zipkin driver and an application insights driver that we wrote. And both of those are built on top of Akka.net as well. We've had some experience building like client drivers before with Akka.net under the covers, but this has been a total pleasure for me to work on. I've really enjoyed doing it, and we're gonna make a lot more YouTube videos about it in the near future. If you're interested in our roadmap and taking a look at some of the things we're working on, I've got 3 epics right here. One for talking about basically wrapping up these 2 different versions of the protocol. But the really fun one, and I look forward to doing a community stand-up on this because our next Akka.remote transport will be based on this as well, is implementing MQTT over Quick. Quick is basically the protocol that is responsible for implementing HTTP 3. So it's going to have wide adoption in the future, but it allows us to solve some of the performance problems that Akka.remote has, such as head-of-line blocking, by taking advantage of multiplexing and also doing away with some of the baggage that TCP has. So that's going to be a lot of fun. So I look forward to doing another video on that at some point down the road. Gregorius, Gregorius, or any of our attendees, you guys have any questions about anything I've done here?
No, I mean, I've looked at your code, so
yeah, I mean, you've actually contributed a bunch of fixes already.
yeah.
So yeah. But any of our end users have any questions or comments? MQTT plus Quick. Yep, it's going to be a good time. There's only a handful of brokers that support it right now. A NanoMQ, which is also made by EMQX, does support it. So we know there is broker-based support out there, but it's still pretty early. But yes, we are going to do Quick. So if we can get 225,000 QoS1 messages over TCP, I'm expecting we can probably do, depends on how big you dial up the number of parallel channels over a quick connection, but we could easily clear 1 million, I think, messages a second that way. So we're hoping to basically get a bunch of users that are doing large scale IoT stuff to give our library a try. Obviously, we have a lot of features we need to add, such as transport layer security and MQTT 5 before maybe some production users can consider it, but we're trying to get there. So that'll do it for this week's Akka.net Community Stand-Up. We will catch you in the month of June. Please don't forget to go and comment on that log filter feature. We're planning on shipping that by end of day Friday. So if you have any last minute feedback on how we should design the API or any performance concerns, speak now, forever hold your peace. Otherwise, I guess we'll see everyone in a month. All right. Take care, everybody, and have a good one.